This section is going to give us an introduction to our basic trig identities. An identity is something that is known or proven to be true. You assume in these cases it's true. So a lot of these identities we have already learned. So first we see our reciprocal identities, and these are our identities that deal with sine and cosecant, cosine and secant, and then tangent and cotangent. So these identities you should already know, but you make sure that you have them memorized. The next set of identities are called our quotient identities. You have also seen these before. So tangent of theta equals sine over cosine, and cotangent equals cosine over sine. So we should be familiar with those. And the next ones, they are going to be new. So the main Pythagorean identity we're going to be concerned with here is the sine squared theta plus cosine squared theta equals 1. Now, I could go into detail, but I'm not going to show you where this comes from, Pythagorean theorem. But this is going to be very important that you have this identity memorized. The other two identities you also need to have memorized, but I'm going to show you a little trick that can help you go from the main identity to these other two. So let's say that I have sine squared theta plus cosine squared theta equals 1. We know that is true. We've forgotten the other two. If I take that first identity and I divide by cosine squared theta, I'm going to divide all of these by cosine squared theta. So all terms are divided by that. And look what I get. Sine squared theta over cosine squared theta is going to give me tangent squared theta. Cosine squared theta over cosine squared theta is 1. And 1 over cosine squared theta is secant theta. So if I do that, it will bring me to that second trig identity, Pythagorean identity that we have there. Now, let's decide that we'll divide by sine squared instead of cosine squared. So sine squared theta and sine squared theta, sine squared, sine squared theta. So if I do sine squared theta divided by sine squared theta, I get 1. Cosine over sine is going to be cotangent, and 1 over sine is cosecant. So I can get these second two Pythagorean identities by using that first one there. Okay. The last identities that you need to have memorized for this section are the opposite angle identities. And they tell us that sine of negative a equals negative sine of a. But cosine of negative a is going to equal positive cosine of a. This happens because, if you think about your quadrants here, I know in the first quadrant, both coordinates are positive. So if we're thinking about the unit circle, this is going to be cosine. The x-coordinate is cosine. The y-coordinate is sine. Now, if I take this a and I make it negative, that flips it over the x-axis. So if I look down here, I know the coordinates are positive, negative. So notice cosine, even if we flip over the x-axis, stays the same. But if sine, if we flip it over the x-axis, it changes sign. So whenever we see something like example 1, sine of negative pi over 6, we know that that is the same as negative sine of pi over 6. And sine of pi over 6 is going to be 1/2, so we get 1/2, negative 1/2 as our answer. However, for number 2, we've got cosine of negative 3 pi over 4. Well, cosine of negative 3 pi over 4 is going to be the same as positive cosine of 3 pi over 4. So cosine of 3 pi over 4. And if I think on my unit circle, the cosine of 3 pi over 4 is going to be negative square root of 2 over 2, because that value would be over here in this quadrant. In that quadrant, you've got negative square root of 2 over 2 and positive square root of 2 over 2. And this would be the value that you would have for cosine of 3 pi over 4. So these are just a couple shortcuts. We will occasionally need to use them whenever we do some verifying trig identities. But basically, it's most useful for just a sort of a shortcut for finding some extra unit circle values. So let's look at how we can use some of these trig identities. One way that we can use a trig identity is that if we know a given trig ratio, we can use that to help us find other trig ratios. They like to give these problems on the ACT, SAT sort of problems sometimes. So if we know that secant of theta is 3 over 2, we're supposed to find cosine of theta. And there's several ways that these problems can be done, but we are going to look at them using trig identities. So first of all, we're going to look back through all of our identities that we know, and we're going to look for any that may include both secant and cosine. And if we look back, right here, we see cosine of theta equals 1 over secant theta, or secant theta equals 1 over cosine theta. But since we're looking for cosine theta, this first one will probably be the most helpful. So I know that cosine of theta equals 1 over secant of theta. And they tell me here that secant of theta is 3 halves. So if I want to know the value for cosine of theta, I just need to do 1 divided by 3 halves. And dividing fractions is easy as pie. We're going to flip the second and multiply, so we will get 2/3 for our answer here. Our cosine of theta equals 2/3. Now these are sort of theoretical problems. They are not asking you to find that angle there or anything. They're just wanting you to be able to relate those two trig identities. Example 2 is a little bit tougher because if we look back through all of our trig identities, I do not see any trig identities that involve both secant and, let's see which one's what we're looking for, cosecant and tangent. I do not see any identities that involve both of those trig functions. So what I'm going to have to do is get a little bit creative here. I do see right here for cosecant that this is involved with cotangent. Well, tangent and cotangent are just flipped. So if I can find cotangent, I should be able to find tangent pretty easily. So this identity is the one that I want to use. 1 plus cotangent squared theta equals cosecant squared theta. So if I start with that, I know if I start with that, I know 1 plus cotangent squared theta equals cosecant squared theta. And some information that I need to make sure that I give you is that when you see cotangent squared theta, what that really means is the cotangent of theta squared. So rather than writing this with the brackets, mathematicians put that little square right behind the cotangent notation there so that we don't have to have these sort of cumbersome brackets here. So when we see cotangent of theta, cotangent squared theta, it means the cotangent of theta squared. So when we plug in, cosecant of theta equals negative 5 over 3. So we're going to plug that in right here. So it's going to be 1 plus, I'm going to write it like this, cotangent of theta squared equals negative 4/3 squared. So this problem we can solve pretty easily for cotangent. So 1 plus cotangent of theta squared equals 16 over 9. We'll need to subtract 1 from both sides. To do that, 16 over 9. We'll have to get like denominators. That'll be 9 over 9. So we get 7 over 9. So that gives us cotangent of theta squared equals 7 over 9. Of course, to get rid of that square, we have to square root both sides. So cotangent of theta equals the square root of 7 over 3. And when we square root both sides, we have to put a plus or a minus here, although I'm going to show you what we'll do with that here in a second. Now, this is cotangent of theta. The problem didn't ask us for cotangent of theta. They asked us for tangent of theta. Well, tangent is sine over cosine. Cotangent is cosine over sine. Or you can think tangent is opposite over adjacent. Cotangent is adjacent over opposite. So if we want to find tangent of theta here, all we have to do is flip this fraction here. So we'd have 3 over the square root of 7. Now the problem is typically our textbook is not going to leave the answer like this. Our textbook is going to rationalize that denominator. So we'd multiply by square root of 7 in the top and bottom. So tangent of theta is plus or minus 3 square root of 7 over 7. Now, you may notice here in the problem, we have this information. Pi is less than theta less than 3 pi over 2. And we haven't really done anything with that yet. But the reason they gave us that information is they wanted us to know what quadrant we're in. So here's 0, here's pi over 2, here's pi, here's 3 pi over 2. So if theta falls between pi and 3 pi over 2, that means that we're looking at the third quadrant here. And if we think of our signs, we know in the first quadrant both coordinates are positive. In the second quadrant, we have a negative and a positive. In the third quadrant, we have a negative and a negative. And in the fourth quadrant, we have a positive and negative. Remember that our unit circle values, our x value is cosine, and our y value is sine. So if we're looking for the sign of tangent in that third quadrant, tangent is sine over cosine, negative over negative, would give us positive. So the answer that we're going to use here for this quadrant is tangent of theta equals 3 square root of 7 over 7. And that will be our answer for this problem. Another thing that can help you remember about these quadrants is this. All students take calculus. This tells us the trig identities that are positive in each quadrant. So in the first quadrant, all identities are positive. In the second quadrant, sine is positive. In the third quadrant, tangent is positive. And in the fourth quadrant, cosine is positive. So that tells us about whether or not sine, cosine, and tangent are positive in each quadrant. So if you notice here, we know we're looking in the third quadrant, tangent's positive, we have tangent, so we choose the positive answer. That can be another way you can look at it. Okay, so that's one thing that we're going to do with these. I know these problems are very theoretical, but we have to know some theory as well. Let's look at the next thing that we're going to be asked to do. So we have sine x plus sine x cotangent squared x, and our problem has asked us to simplify here. So what we're going to do is try to condense this to make it smaller. If we look at our problem here, I notice that I see sine in both of these terms. So what I'm going to do is I'm going to factor sine out like it's the greatest common factor. Just like if I had x plus xy squared. If I had x plus xy squared, I could factor out an x, and I would be left with 1 plus y squared. So just in that manner, I'm going to factor out a sine x. If I do that, I'll have 1 plus cotangent squared x. Okay? 1 plus cotangent squared x here should sort of be jumping out at us. If we flip back to the Pythagorean identities, 1 plus cotangent squared theta equals cosecant squared theta. So, if I go back to that problem, I can replace 1 plus cotangent squared theta with cosecant squared theta. Actually, x's, we're using x's here, not thetas. So, now, cosecant, I know that is 1 over sine. So, sine x times 1 over sine squared x would look like this. And then this equals, if we put this over 1 and multiply, we get sine over sine squared x. Remember, sine squared x means sine of x squared, or sine of x 2 times. So that's like having this. So I could cancel one set of those signs, and that gives me 1 over sine x. So this would simplify all the way down to 1 over sine x. After that, there's really not anything else you can do with the problem. Let's look at our next problem. We've got 2 minus 2 over cosecant squared theta. So in this case, I know cosecant squared theta is the same as 1 over sine squared theta. So I have 2 minus 2 over 1 over sine squared theta. What that's really going to do is 2 minus 2 times sine squared theta over 1, which is going to give me 2 minus 2 sine squared theta. Now, here we have a 2 that we could factor out, so that would give me 2 times 1 minus sine squared theta. Now, we haven't seen this yet, but this should be something that eventually we start to notice a lot here. 1 minus sine squared theta. This is sort of an identity. I know, this is sort of a side note here, I know that sine squared theta plus cosine squared theta equals 1. That's my Pythagorean identity that usually most kids are pretty good at remembering. So if I take this and manipulate it a little bit, if I subtract sine squared theta from both sides, then that tells me that cosine squared theta equals 1 minus sine squared theta. Now notice that these two things right here match. So that means I can replace 1 minus sine squared theta with cosine squared theta. Now, this is not a separate identity here, this cosine squared theta equals 1 minus sine squared theta, because it comes from the Pythagorean identity. But we need to watch out for this because we need to have it memorized like it is an identity. In a similar manner, we also need to know that maybe if we had subtracted cosine instead of sine, that in this case, sine squared theta equals 1 minus cosine squared theta. So those are two identities that aren't separate identities. They come from that Pythagorean identity, but we need to know. So we have simplified this down all the way to 2 cosine squared theta, and there's not much else that we can do after that. Let's try another one. Sine x plus cosine squared. Sine x plus cosine x squared plus sine x minus cosine x squared. Now, be careful with this problem because you might be tempted to say that this is sine squared x plus cosine squared x, but you cannot do that because when we see sine x plus cosine x, that means sine x plus cosine x times sine x plus cosine x, like this. And when we see sine x minus cosine x squared, that means sine x minus cosine x times sine x minus cosine x. So here we have to FOIL this out. We'll get sine x times sine x is sine squared x plus sine x cosine x plus sine x cosine x plus cosine squared x. And then we also have to FOIL here, so we'd have plus sine squared x minus sine x cosine x minus sine x cosine x. I'm running out of room here, plus cosine squared x. So you should notice here I have a positive sine x cosine x, and over here I have a negative sine x, cosine x. Those are going to cancel. I also have another set of those that will cancel as well. So that leaves me with sine squared x plus cosine squared x plus sine squared x plus cosine squared x. I can combine those sine squared x and cosine squared x's if I want, but look at what we have here. We've got sine squared x plus cosine squared x. That is one of our Pythagorean identities. Sine squared x plus cosine squared x equals 1. So we can replace this set right here with 1, and we can replace this set right here with 1. 1 plus 1 equals 2. So this simplifies all the way down just to give us 2. Okay. And here's our last example that we are going to do. Here we're also going to have to FOIL. So if we multiply, we get cosecant x minus cotangent x, and then we get plus cosine x times cosecant x, and then we get plus cosine x times cotangent x, and actually that should be a minus sign that goes right there. So cosecant and cotangent we can't do too awful much with right now. I'm just going to leave those. But let's remember that cosecant x is 1 over sine x. And let's also remember that cotangent x is cosine x over sine x. Okay? And actually, I'm seeing with all these sines and cosines, it might be helpful if we went ahead and changed our cosecant and our cotangent. So this is a strategy we'll use sometimes. Cosecant is 1 over sine x. Cotangent is cosine x over sine x. Alright, so if I look at what I've got here, I've got 1 over sine x minus cosine x over sine x. Right here, this is going to be plus cosine x over sine x. And then I'll have minus cosine squared x over sine x. Now we should see here I've got a positive cosine x over sine x and a negative cosine x over sine x and a positive cosine x over sine x. So these two terms will cancel out, giving me 1 over sine x minus cosine squared x over sine x. And because these have common denominators, I can write them like this: 1 minus cosine squared x over sine x. Now remember, back a couple problems ago, we said that 1 minus sine squared theta equals cosine squared theta, and 1 minus cosine squared theta equals sine squared theta. So, right here, this 1 minus cosine squared theta, I can replace with sine squared x, and sine squared x over sine x looks like this. That is sine x times sine x over sine x, and one of those will cancel, so we get this all the way down to where it is simplified just to equal sine x. So often we'll have a complicated equation at the beginning and we'll end up with just a very simple trig solution at the end. We will do this assignment in class. You don't have to do it for homework. The homework is just to take these notes. But in class, we're going to do this assignment, page 4, 28, 25 through 35 odd, and 44 through 53. And on Wednesday, we will have a quiz on the identities. It'll just be a blank quiz on memorizing the identities. So all of those identities at the beginning of these notes will be on that quiz that we have